Beijing just put a lot of pieces on the table in a very short time. Humanoids debuted, an Olympic-style venue was prepped for autonomous football, a robot mall opened its doors to everyday shoppers, and a research team used generative AI to assemble a drone's control system in mere days. Individually, each of those moves would be news. Together, they form a single narrative. Robotics is leaving its lab-focused, slow-moving past and stepping into a fast, commercial future. This week felt like a concentrated push. Research, retail, competition, and software automation, all aligned around the same idea: make robotics normal. It's hard to overstate what the juxtaposition means. A humanoid that's modular and accessible, an arena where robots compete in front of a public audience, a physical mall selling robot services and units, and code generation tools that can scaffold airborne systems in weeks. Put another way, hardware, software, market, and spectacle were synchronized in a way we rarely see. That's the shape of systemic change, not one breakthrough, but many, appearing to accelerate each other. The rest of this script walks through the technical details, the theatrical moments, the business signals, and the safety questions that come bundled with speed. But first, let's meet the robot that kicked off the conversation. But let's start at the machine that kicked it off. Meet the LimX Oli. Short description: about 1.65 meters tall, roughly 5 feet 5 inches, built with 31 active degrees of freedom and designed for modular upgrades and real-world tasks. That phrase, designed for modular upgrades, is the important part. Many humanoids in recent years have been research platforms, impressive for demonstrations, awkward for real work. Oli is pitched differently. It's modular at both the mechanical and software levels, with a clear interface for third-party peripherals. For developers, that means you can swap in different end effectors, plug in sensors, and run custom code without changing the robot's core architecture. For buyers, it means a single base unit can be adapted across many roles: education, validation, customer service, or light industrial work. In practical terms, Oli supports 2-finger grippers and fully articulated 5-finger hands. It supports additional cameras, microphones, tactile skins, IMUs, and other sensing hardware. The SDK exposes joint-level control and full-body state so teams can build imitation learning pipelines, teleoperation systems, or entirely autonomous behaviors on top of a known baseline. The debut at the World Robot Conference wasn't accidental. The platform wants to be visible to researchers and industry buyers at the same time, to invite both community contribution and commercial partnerships. And that hybrid positioning is one reason Beijing's events are significant. It's not just a new body, it's a new way of building bots. 31 degrees of freedom is a technical detail that maps directly to what a robot can physically do. Each degree of freedom is another joint or axis the robot can control. More axes mean more subtle, natural, and complex motion. Think of a human hand and wrist. The ability to twist your wrist slightly, to angle a fingertip, or to flex a thumb independently is how you manipulate delicate objects. For robots, those mechanics are represented as DOFS. 31 degrees of freedom lets a humanoid coordinate torso, limbs, wrists, fingers, and head in ways that mimic human-like intent. That matters for dexterity, or the difference between picking up a box clumsily and performing a precise task like unlatching a handle or typing on a screen. It also matters for balance. When a robot can redistribute its joints in micro-adjustments, it recovers from pushes and missteps more gracefully. Beyond tasks, DOFs change perception and planning. More degrees require more complex control loops and better sensing, but they also open possibilities for smoother human-robot interaction and safer manipulation in cluttered, unpredictable environments. In short, movement richness leads to practical usefulness. That's the step Oli is aiming to make. So what can Oli actually do in the real world? Oli's hardware choices are practical, not just PR friendly. A 2-finger gripper can handle many routine tasks like opening doors or carrying plates. A 5-finger hand enables dexterity for tasks that require precise grips. Importantly, these are not permanent decisions. Developers choose what fits their use case. The Open SDK is equally consequential. It exposes sensor streams, joint states, and task orchestration interfaces. That means teams can develop imitation learning routines in simulated spaces and transfer them to the physical robot with fewer changes. It means remote updates and motion library pushes become part of how a robot improves over time. Cloud APIs combined with local control provide a pragmatic balance, keep critical control loops on device for safety and latency reasons, but allow new behaviors and motion libraries to be uploaded remotely. Onboard support for large language models enables natural language interaction that ties meaning to motion. The robot can interpret commands and translate them into coordinated, embodied actions. All of that is about reducing friction, fewer tech black boxes, better upgrade paths, and a developer experience that feels modern. This product strategy explains why the manufacturer chose a major public conference for the debut. They want both ecosystem adoption and investor attention. And those design choices explain why Beijing chose to debut it now. The World Robot Conference is one of the major industry stages where academic projects, startups, and established players meet. It's not just a series of demos, it's an event where partnerships are brokered and funding conversations begin. Revealing a platform like Oli at that conference signals readiness beyond the hobbyist level. For an ecosystem to flourish, you need developers, test environments, customers, and capital. WRC provides a single place where those groups can meet and test assumptions publicly. And this year, an expanded set of exhibits and public demos created a narrative that robotics is moving faster than many expected. If you're a researcher, you see new hardware you can test your algorithms on. If you're a buyer, you see a product you can imagine deploying. If you're a policymaker, you see a public-facing demonstration that raises practical questions about standards. All those perspectives make a conference reveal more than PR. It makes it part of a market transition. But the conference itself was only the start, and the games turned it into theater. The World Humanoid Robot Games are less like a tech conference and more like an athletic festival for machines. Hundreds of humanoids, dozens of teams and disciplines, ranging from sprints to combat and human-robot integration demonstrations, compress into a few days of intense competition. That scale shifts the event from gear shows and lab demonstrations into an ecosystem test where many designs meet real-world constraints. For the broader public, a robot sprint or a humanoid dance routine is a captivating spectacle. For engineers, the competitions force cross-team comparisons under shared rules and conditions. For startups and investors, it's a place to spot emergent winners early. The overlap matters. Public attention can accelerate venture interest, which accelerates manufacturing, which accelerates deployments that, in turn, shape public expectation. Framing robotics as sport does something else. It normalizes the presence of humanoids in shared spaces. When you watch a robot race or play a match, you start to picture one sitting at a restaurant or delivering packages, which is exactly what these events want to encourage. And the headline act was as dramatic as the press suggested. The 5 vs 5 humanoid football match is a milestone because it layers perception, planning, and coordination at a scale rarely attempted outside labs. Each robot needs to localize itself, predict ball trajectories, coordinate with teammates, and react to opponents, all in real time. There's no human pilot overriding decisions mid-game. That constraint forces developers to confront latency, sensor noise, and decision arbitration in an environment with unpredictable dynamics. Importantly, staging this match in an Olympic-style venue introduces factors often absent from controlled lab settings: variable lighting reflections off surfaces, acoustic noise, and a human audience. All of those are edge cases that can break perception pipelines. A robot that performs well in a lab can behave very differently in a stadium. The organizer's choice to run the match publicly isn't just spectacle, it's research at scale. It accelerates learning by exposing systems to real-world messiness at once, rather than through long, staged tests. That's risky, but also instructive. Watching these trials play out gives engineers data and the public a tangible sense of progress. Before the ball even kicked, teams had already learned something new. Smaller matches and prior Robo League finals revealed patterns that teams had to address: brittle perception in changing light, fragile locomotion under uneven surfaces, communication failures between agents, and difficulty maintaining formations under external perturbations. Many early competitions were dominated less by creative strategies and more by which team could engineer robustness into perception and state estimation. Scaling from 3 robots to 5 increases combinatorial complexity. More agents mean more interactions, more occlusions, and more prediction tasks to solve simultaneously. The algorithms must not only be fast enough to run in real time, but also conservative enough to avoid collisions. That trade-off between aggression and safety becomes visible in gameplay. Teams that played defensively often outperformed those that tried risky maneuvers. These matches serve both as a stress test for algorithms and as a development lab for communication protocols. In many ways, the sporting metaphor is accurate. You need endurance, strategy, and coordination. And all three are as much software challenges as hardware ones. Scale matters. So do the conditions in which you stage the test. Panda I is more than an architectural flourish, it's infrastructure tuned to the needs of robots. The dome's geodesic structure, combined with a specialized membrane, controls temperature, humidity, and particulate levels, conditions that directly affect sensor performance and mechanical wear. For teams experimenting with high-precision perception systems, having a predictable environment is crucial. Next to the stadium, the training base functions as a living lab. Engineers can iterate quickly in a setting designed to simulate real-world variability while keeping some variables controlled. This is essential for repeatable experiments and for building datasets that reflect both performance and failure modes. From a strategic standpoint, having dedicated hardware-friendly venues signals an intent to professionalize the field. When you build infrastructure, you remove friction for teams to test more often and to scale their work faster. That, again, accelerates the cycle from prototype to deployment. While competitions showcase engineering, Beijing also moved on the consumer front. The Robot Mall flips the narrative from lab-only to consumer accessible. Walking through its floors, shoppers don't just see concept robots, they can interact with working units, buy hardware, schedule maintenance, and even experience robot-driven services like restaurant cooking or table service. It's a retailized service approach to robotics, the same model that transformed cars from rare luxuries into everyday transportation through dealerships and service networks. The product spectrum ranges widely. Small domestic helpers at low price points, more capable service robots at mid-price tiers, and full humanoid systems at premium prices. The presence of spare parts and maintenance services is key. It acknowledges that robots are products with lifecycle costs, not one-off gadgets. This commercial framing changes everything. Consumers will expect product warranties, updates, and support. Perhaps most important, it places robots into normal consumer behavior. People who visit the mall are not researchers. They're shoppers evaluating convenience, novelty, or entertainment value. That soft normalization is as powerful as any technical improvement. Once the idea of a robot waiting tables or playing chess in a mall becomes familiar, it lowers psychological barriers to adoption elsewhere. That commercial push is backed by serious capital and policy priorities. Public reports highlight large-scale policy and funding initiatives aimed at accelerating AI and robotics development. Subsidies, venture capital flows, and stated government goals combine to lower the barriers for startups and established firms alike. When those incentives align, the ecosystem changes. Manufacturing ramps up, supply chains form, and service ecosystems, like maintenance and parts suppliers, appear. Large funds and subsidies are not neutral. They shape priorities. Rapid scale-ups are rewarded, and that changes the calculus for founders and researchers. If you can access capital to move quickly from prototype to factory, you can capture market share and set standards by default. Conversely, that same momentum can marginalize slower, more cautious approaches unless regulatory frameworks ensure safety and accountability. From a macro perspective, large public investment signals a strategic push. Make the country a leader in robotics by removing friction across funding, infrastructure, and public demonstration. This is a classic industrial policy playbook, and it's accelerating capability diffusion in ways market forces alone may not achieve. Which brings us to a very different kind of speed: how quickly code can be produced now. In California, a research team demonstrated an AI-assisted approach to building a drone's control system. The project, which generated roughly 10,000 lines of code in around 100 hours, combined multiple AI models and tooling to scaffold firmware, mission planning modules, and a higher-level AI layer for obstacle avoidance. They ran sprints using tools like VS Code, AI copilots, and different LLMs, iterating until the stack ran on a Raspberry Pi-based drone. The three-layer architecture, low-level flight firmware, intermediate planning and mapping, and high-level AI-assisted avoidance is familiar in robotics. What's different is the generation method. Using generative models to produce initial code dramatically shortens the time from concept to flying prototype. Where a previous all-human effort took years, this new pipeline produced a working system in weeks. but the details matter. Context window limits, model hallucinations, and hardware constraints required significant human oversight and refactoring. The models produced scaffold code, but human engineers still did the heavy lifting of integration, safety checks, and optimizations. Rapid creation is exciting, and it raises hard questions. The practical implications of rapidly generated code are complex. On the one hand, faster prototyping lowers cost and allows more iterative testing. On the other hand, speed can mask shallow testing or hidden assumptions. Models can produce plausible-looking code that fails in edge cases or misinterprets requirements. Context window limits can fragment logic across multiple model runs, creating brittle stitching points. In military or critical infrastructure contexts, that brittleness is unacceptable. Even in consumer drones, unexpected behavior can cause property damage or injury. The point isn't to demonize generative approaches, they're powerful and useful, but to highlight that quality assurance and rigorous testing become even more important as development speeds increase. Industry voices are clear. AI-assisted coding is a tool, not a replacement for engineering discipline. The appropriate response is to invest in verification, simulation, and controlled deployment pipelines. Build fast, yes, but validate harder. Faster development changes incentives and risk profiles quickly. When capabilities accelerate, governance must adapt. Experts broadly argue for three parallel tracks: standards for testing and verification, transparent reporting of capabilities and limitations, and regulatory guardrails for deployment contexts. Those suggestions are practical, require robust simulation testing for autonomy, mandate logging and explainability for decision-making systems, and restrict deployment in high-risk scenarios until sufficient safety evidence exists. It's important to frame these concerns without jumping to sensational conclusions. The goal here is proportionate caution. Identify likely failure modes, model misuse scenarios, and build mitigations, rather than impose blanket bans that would also stifle beneficial innovations. Policymakers and industry must collaborate on standards that are technical and enforceable. Part of that work is public communication. Events like the World Robot Conference and Robot Mall increase public visibility. That visibility helps stakeholders align on acceptable uses and public expectations, but it also requires clear explanation of what these systems can and cannot do today. Overpromising harms trust and adoption. That tension between capability and safety will shape public discourse this year. For researchers, modular platforms and open SDKs lower the cost of experimentation. For entrepreneurs, visible marketplaces and investor interest create path to market clarity. For hobbyists and students, cheaper hardware and public exhibitions make robotics feel within reach. For policymakers, rapid capability increases demand, clearer standards, and more active oversight. For consumers, the idea of robot as product is becoming tangible. Each group gets different signals, but the overall message is consistent. Robotics is entering a phase where deployment matters as much as demonstration. That shift will bring both opportunity and friction. Opportunities for new businesses and services, friction in the form of supply chain, standards, and ethical debates. Understanding who benefits and who is at risk will define the policy choices the next few years must embrace. Put simply, many doors just opened and they swing both ways, and that sets the stage for a surprising final take. Beijing's week felt like a coordinated statement. Showcase a modular humanoid platform, stage mass competitions, open a mall where robots meet consumers, and highlight AI-assisted development that can accelerate timelines dramatically. The combined message is strategic. Normalize robotics, accelerate industry formation, and invite global attention. The possibilities are exciting. Better tools for the elderly, automated manufacturing assists, new classes of service robots. The risks are real too. Rushed deployments, insufficient testing, and governance lag. The balance between these outcomes depends on how industry, government, and civil society respond. So here's the simple question to leave viewers with. Are we watching a productive democratization of robotics or a hurried transition where mistakes could be costly? That's the conversation we need. Drop a comment with what excites or alarms you. I'll read everyone. Thanks for watching. If you want longer, more technical breakdowns of any section, say which one and I'll dive deeper.